The numbers will grow, so in the future, come a little bit early and make sure you grab your cookies and coffee before other people figure out that that's what's here. I'd like to let you know about next week's colloquium, and it is the 11 best math problems ever by Megan Taylor, who is at Stanford University right now. And I saw that talk when she had 30 of the best math problems ever, and I said, can you pick your 11 favorite? Well, actually, I said pick your 10 favorite. She couldn't get it down to 10. But they're very, very fun problems and a wide range of ability levels and interest, and they're not straightforward, and so they're very fun. So I encourage people of all math levels and interests to come. We are trying to see if we can get these colloquiums posted on YouTube. So we're still in the process of working that out, and we'll give you further updates as that happens. But they're usually available in a week or two from the math office if you want to re-see one of these colloquium talks or inspire some of your friends to come see a great talk that you witnessed. And now, without any further ado, I'd love to introduce this fabulous talk for today from Dr. Brennan, Ford, and Newman. Now they're in alphabetical order, which is fabulous. And normally I would tell you great things about their past and their education, although no. But today I want to tell you that this talk happened as of Friday afternoon. So Friday afternoon, you might notice that the talk title there does not match the title on the pink sheet, and that's because the colloquium speaker on Friday said there was a family emergency and couldn't make it. So by Friday at 3 o'clock, these three fabulous individuals had volunteered to put together this talk by today for you. And so I thank them very much, and I will let them tell what they're going to say. Thank you.
There's a backstory on that, too.
I don't know what the story is of why Benjamin Wells couldn't be here, but so we're going to show you some things that we put together a couple of years back for a program we did in the Lifelong Learning Institute, which is a program that Sonoma State puts on for interested adults in the community who just want to learn some stuff for fun. They're not after degrees. It's a lot of fun to teach in because there's no exams and no grading, so that makes it a lot of fun. So first we're going to start by showing you a little bit about some of our mathematical heroes. So this is always good advice, pay attention to the classics. There's always a lot to learn. So let's see how this works.
What's the percentage? I figure 75% to you, Mom, and 25% divided between the five of us. Gina, Crowbar, myself, Tom, and the baby. That makes 5% for each one of us.
No, Billy, you're cheating yourself. If there's 25% divided among the five of you, that's 14% apiece.
Oh, no, listen, Pa. I wouldn't cheat you. You know I wouldn't. Now, look here. I'll show you. Let me rub this out here. And now, 25 divided by 5 is 5. You see, the 5 won't go into 2, will it? No. But 5 goes into 25 5 times, you see?
No, you're wrong, Billy. Now, I'm pretty good mathematician. Now, 5 into 25, 5 won't go into 2, will it?
No.
But 5 goes into 5 once. Now, we didn't use the 2 before, so we're going down here. Now, 5 into 20 goes 4 times. There you are. 5 into 25, 14.
No, look, Pa. Let me prove it to you now by multiplication.
There's going to be a quiz on this method, so pay attention.
Times 5. 5 times 5 is 25.
I'm surprised you're learning.
Huh?
I'm surprised that you're learning. Now I'll show you. 5 times 14 is 25. 5 times 4 is 20. 5 times 1 is 5. 25. That's it.
No, look, Ma. Look, you're wrong there because I'll prove it to you. We'll put down 5 14s here. 14. There. Now I'll prove to you by addition that 5 14s is not 25. 4, 8, 12, 16, 20.
21, 22, 23, 24, 25. There you go. Press up, Billy. I want to see you boys cheating.
So, let's see, Ma and Pa say that 25 divided by 5 is 14. Then they go on to show that 5 times 14 is 25. And finally, the 14 plus 14 plus 14 plus 14 plus 14 is 25. So figure out what their strategy is. See if you can figure out what they're doing and test it on 28 divided by 7. See what you come up with for 28 divided by 7 using their division strategy. So work that out for a minute. And if you need a colloquium poster, you can use the back of it for this talk and then post it later. Anybody want a poster?
Poster to write on. This is active.
Okay, according to their
Okay,
7 divided.
hold on, give everybody a chance. 28 divided by 7.
Anyone else need something to write on? Figure out their strategy. Repeat it. It is repeatable.
Feel free to talk with your neighbors. Don't shout it out so everybody can hear.
Yeah.
See if you have the same idea of what they're doing as your neighbor. Okay, so we got any guesses as to what they're going to get?
13.
13? Somebody said 31? Not some similarity there. Those two numbers have the same digits. Any other potential? So how are we getting the 13?
7 divided by 28 is 13. 7 won't go into 2, but it will go into 8.
One time, okay.
One time. 8 minus 7 equals 1. Bring the 2 down is 21. 7 into 21 is 3. 13.
So 1 free, okay. Can everybody picture Ma and Pa? Is that think what they'll do? Okay, so Ma and Pa had some students, and we'll see them working out their mathematical skills
No,
now.
Snoopy, no. Oh, come on, one don't.
I can't afford it. I just made 28 of these things. I mean, after all, 7 offices I got feed. And I got just enough to give them, 13 apiece. You want what? 13 apiece.
13 apiece?
Yeah, this
7 offices.
Yeah.
Each has 13. You only got 28.
That's right. I got $28 and 7, 13. I gave you
7 13s is 28.
Yeah.
That's ridiculous.
It's gotta be right.
7 times 4 is 28, not 7 times 13.
7 times 4 is 28.
Sure.
7 times 4 is 28. What's going to go cheap school? I mean, 7 times 13 is 28.
That's ridiculous.
Yeah, figure it out.
What's the matter with you?
No, I just want to figure it out. Don't get it.
You had it.
I figured it out myself.
Prove that to me.
I'm not fooling you. Don't worry.
Ridiculous.
No, it ain't. No, it ain't.
Oh, come.
No, it ain't. It's not ridiculous.
No sense to your argument.
That's so.
Go ahead.
You'll stay. Now, there were 7 officers.
That's right.
There's a 7. Now I'm going to divide and prove it to you. Now, $28.
28 don't. Now, wait a minute. You claim the 7 goes into 28 13 times?
Mhm.
Prove it to me.
Now, 7 to 2.
What do you mean 7 to 2?
7 will not go to 2, no matter how much you try.
We know that.
You couldn't even push that big 7 that little bit.
So why not?
Therefore, we can't use it too.
What are you doing?
I'm gonna let Dizzy hold it. Dizzy, you hold that 2 for me, will it, please? Thank you. I'll use it later.
What is this all about?
Now, 7 to 8, 1.
One.
Now, we're gonna carry the 7.
Carry the
We're
7.
gonna carry the 7.
Carry it.
It's getting a little heavy, so put it right down there. 7 to 8, 1. Now, a minute ago, we didn't use it 2.
What do you mean?
We're gonna use it now.
Use it.
Dizzy, give me back the 2. Thanks. Put it right down there.
So?
See? Now, 7 to 21?
3 times.
3 times. 7, 28, 13.
Oh, now wait a minute. Come here. You never go to school, stupid.
Yeah, I come out the same way.
Oh, never mind that. Multiply this.
Yeah.
Put down 13 up there.
Down 13?
Yes. Now, you claim that each officer gets 13 donuts.
Now,
Now, wait a minute. I have 7 officers. Put down 7.
7,
Draw a line.
Sure.
Now, 7 times 13 is what?
28.
Prove it.
7 times 3,
21.
7 times 1,
7.
7 and 1,
8.
2.
Oh, no. Well, it shouldn't come out right.
It's gotta come out right or I go on the break. God, I know.
Just a minute. We'll add this up. Put down 13 7 times.
Okay.
We'll add it up.
That's
straighten
1,
this out.
2, 3, 4, 5, 6.
No, wait a minute.
Oh, I forgot dynamite.
Yes.
I don't want to forget dynamite.
No, there's 7 officers. Now we're getting. Now, you claim all this added up amounts to what?
28.
Give me the chalk.
No, you take the spot from right.
Sure, there's something wrong here. 3, 6, 9, 12, 15, 18, 21.
22, 23, 24, 25, 26, 27, 28.
Oh.
See?
All hands on deck. Order listeners today, everyone. All hands on deck.
I mean that.
All right, so with such mathematical luminaries, let's let's investigate what Lou is doing there. So I put these up here in a different order. So we'll look at multiplication first. So what I'd like you to do with a neighbor is one of you try to write down instructions for multiplying a one-digit number by a two-digit number correctly, and the other one try to write down the instructions for what Lou does. So decide which of you wants to quickly write down some instructions.
I have to understand these things, so I guess, multiply one digit number by two digit number. Put 13 on top and multiply time and 7. Multiply 7 by, take the top number and divide it into two separate numbers and multiply 7 by each one. And go 7 times 3 is 21, and then put the 0 down, 7 times 1 is 7.
So what do you think? What's the problem? But when he does the 7 times 1, 7, what's the problem?
You didn't put the 0 in front of it. You have to move it over a place.
So it's 7 times 10.
Yeah.
It's not really 7 times 1.
Yeah.
It's treating it like 7 times 1.
I don't care what they say, this is not a cheap school.
I want to know when they stopped doing division with that thing on the right. Does anyone here remember doing division that way? Bill, did you do it that way in school?
No.
Because it looks like they're all doing it that way,
The way that's,
but I've never seen it done that way.
yeah. That was maybe Republic Pictures.
Right.
Both the same.
Samuel Goldwyn.
Okay, does anybody have some instructions they could read out for how to multiply a one-digit number by a two-digit number correctly? Or if you haven't finished writing, just tell us what the directions are.
You know, you did it really well. I think you should volunteer.
Well, unless I'm a big student.
Oh, you're not a student?
He's actually part of our talk here.
Uh-oh, I cheated.
That is the right answer. 1 and 3 is 4.
Anybody got instructions for multiplying a one-digit number by a two-digit number?
Can I maybe volunteer? No one else?
Sure, give it a shot.
I asked the teacher, when they're multiplying the 7 times 1 and making 7, that 1 is in the tens place, not the ones place. There should be 7 times 10. And there should be a 0 in front of that 7, so it would be 70. And then you add them together, and you get, like,
91.
Right, so I'm not getting any volunteers for how to multiply.
You have to carry the 2 over the 1, the 1 times 7.
So let's just look at how this procedure compares with what you hear kids doing when they're multiplying, right? What would you hear a kid doing when he or she was multiplying 7 by 13, say, correctly?
There's a blank.
Can I use a blank slide here?
Yeah.
Well, I don't want to mess up.
I just found it.
So what would you hear?
3,
7 times 3 is 21.
1, and carry the 2.
Okay.
7 times 1 plus 2.
Okay. So there's our kind of abbreviated version, and then there's a slightly expanded version that they do a lot in schools these days called partial products or something like that, where you'd say 7 times 3 and you'd actually write down the 21. And then
7 times 10.
you do, yeah, so here you often hear people say 7 times 1, and then they just write it in a different place. Or if you're thinking of it as a 10, you'd say 7 times 10 and write a 70. One method of saying that sounds an awful lot like what Lou was doing here, and it's, you know, that little bit about where you write that 7 is kind of, if you're thinking just procedurally, it's pretty hard to get across why one is correct and why the other one isn't. So what's your name?
Patty.
Patty's already went through this a bit for the first one, explaining why Lou's procedures don't give us any correct result. And as Steve pointed out as well, it essentially comes down to thinking of that 1 as a 1 instead of a 10. Or I guess maybe Dr. Wilson was thinking in this example. I'm not sure. Okay, so I haven't been able to find more modern movies that have that same example in them, but it's kind of funny that they both did exactly the same thing.
There are 2 different movies?
Yeah, two completely different sets of comedians that, I mean, clearly one stole from the other, but I don't know which one of those 2 came first. All right, let's see.
Loves company.
Yeah. So, okay, here's this bit about the 1 being a 10, not a 1. And so writing that 7 down in that 1's position didn't work. And it really is the same error or the same idea in all 3 methods. But usually, if you come across a problem working with a child trying to understand arithmetic, usually if you can look at it from another angle, the other angle will point out the fault in the first attempt. And so having all 3 of these confirm each other is quite a feat to be able to put that together. Okay, so we're ready for mind reading.
All right. See, we're still attached to the internet.
Should I click it?
Yeah.
Okay.
Oh, good.
So far.
All right, so we found this special website. The computer out there can read your mind. You always worry about this, but in fact it is true. This special website will be able to read your mind. So let's play a little game, and I'm going to prove to you that I can read your mind. Okay. We weren't sure that those directions would be clear from the audience on the web, so we just redid these numbers. If I could have a brave volunteer from the audience to allow this computer to read your mind. Great. All right. Okay. So, all right, we're all going to be focusing on you, and you're going to be, allowing the computer to read your mind. So let's go through this little game here. All right, so choose any 2-digit number. Not one of those up there, just any, well, I mean, it is going to be one of those.
65.
65. Okay. All right, so you picked 65. Let's add together the digits. So that's 6 plus 5 equals 11. And now what we're going to do is we're going to take this 11 and we're going to subtract it from the 65. What do we get?
54.
54. Great. Okay. All right. We have our number. Now I want you to find that number up on the screen somewhere. Do you see it?
Yeah, it's
And yeah, it's up there. Great. And focus on the symbol to the right there, Sam.
Oh, right.
Yeah. And I want you to put that symbol clearly in your mind.
All right.
Maybe everybody, we can help him. Okay, everybody, we can help him. Symbol clearly. And let's see what the mind reader can do for us. Was that your symbol?
That was it.
That was amazing. Wow, okay, all right. So does everyone understand the instructions, what we're supposed to do? Okay, so now we're going to try to trick the computer, okay? If all of us are thinking at the same time, maybe it won't be able to read any one of our minds. You think so? Okay, so what I would like everyone to do, think of your own favorite 2-digit number. Don't shout it out, just think of your 2-digit number. I want you to go through this process. So you might want to get out your pencil because you want to do this correctly. 2-digit number, add together both digits, subtract the total from your original. Okay, begin focusing. Find your number on the screen there. Find your number.
Find the number after you subtract.
After you subtract. Yeah, not your original number, this number after you subtract.
Stare at it.
And stare at the symbol to the right of the number. So if your number is 10, after you've done the subtraction, stare at the symbol, okay? So has everyone got your symbol in mind? Everyone's focusing really hard.
I'm gonna draw a picture of one of the things
Okay, all right, yeah. Maybe draw a picture on your page, stare at it, focus.
for evidence.
Okay, everybody's ready?
How many people had that? symbol?
Good gravy.
Really?
Oh my God.
Whoa.
You had that symbol? Everybody had the same symbol? Is that something
I
the
think we should do it
computer
one
is
more
doing?
time.
I think that might be
One more.
something the computer is doing. It's influencing your mind.
Let's do one more.
Okay, all right, let's do it one more time. Pick your second favorite two-digit number.
You know what?
Pick your second favorite two-digit number. Second favorite. Take the sum of the two digits, subtract it from the original number. Oh yeah. Okay, all right. So but let's make sure everyone's doing the arithmetic. We don't want the computer to try to, mess with our brains when we're doing the arithmetic, right? Okay, so find your symbol, find your number after subtraction, and look at the symbol to the right. So if your number after the subtraction was 31, that's the symbol you focus on. Okay, is everyone focused? We're all good? You're thinking hard?
Go. One second, here we go. How many people had that symbol?
Woo!
Okay.
I don't know, I'm a little disturbed about this. Pretty creepy, okay. All right, well, so we noticed, we observed a couple of things. Everybody had the same symbol. Can somebody start telling me what some of those numbers were? Like, after you got to this point here, where you have your final number, can somebody tell me what your number was that time? Yeah, what was your number?
Okay, but no.
Oh, no, I don't want the trick.
All right.
What was your final number? 9. It was 9? What else? Did somebody else have a different final number?
81.
81?
27.
27?
54.
54? 63? Did anyone have a number that, wait, what?
Any other numbers?
Any other numbers? Oh, can you guys give me
They
It was
can't
probably
do
in
54,
there.
you already
72.
did 54.
I think still could.
72, right?
72?
And it's like 45,
45?
36.
36?
No, I mean, did you have
I can generate.
I just
that
fell off the
number.
horse.
So what do you notice about these numbers that they have in common?
Multiples of 9.
Multiples of 9.
Multiples of 9.
Multiples of 9.
Where did the multiples of 9 come from? So let's take a look at can I put the, notice that the computer cleverly removes the list of symbols and numbers there. What do you notice about the symbol next to the 9?
You're all the same.
And the symbol next to the 18? And the symbol next to the 27? And 36? And,
But it's also next to the 19.
oh yeah, it's next to the
Everything
19.
else is random, but they set the ones next to the number.
Yeah, but
What about 90?
and 99. Those
And
are multiples of
99.
9.
Well, the thing is, you need a 3-digit number to subtract it out to 90.
Ah, somebody is thinking out there. Well, let's see how it works.
All right. So,
Maybe
yeah, why
grab
couldn't
this.
you get a 90?
Why is it possible? Yeah, good question. Take your 2-digit number, subtract the sum of the digits. Why wouldn't you get 90?
Zero.
Why can't you get 90?
It'd have to be greater than 90, what you're starting with, right?
Uh-huh.
And therefore the sum, if the smallest number to be would be 91. So 9 plus 1 is 10, that pushes you out of the 90s for your starting point.
Well, you can start with 99, right? I mean,
But then the sum of the digits is 18, and that takes you below 90.
there's no way you can end up with a sum of 90, everyone agree? And there's no way you can end up with a sum of 99? So they just messed with you and put different symbols there? Okay. So let's look at a few things we noticed. Everyone noticed that everyone had the same symbol. Everyone's number was a multiple of 9. Did everyone notice that your number is really your first digit times 9? First digit of your original number times 9. So we saw that they all have the same symbol if the multiple is 9, except for 90 and 99. Is this a coincidence? Well, we don't think so. We're going to show that every time you subtract the sum of the digits from a number, you'll get a multiple of 9. Some of you probably already discovered why. Let's look at an example. You start with the number 75. You'd subtract the sum of 7 and 5. If you write the 75 as 7 times 10 plus 5 times 1, and then distribute the negative sign, you'll be subtracting 7 and 5. Then you regroup, you got 7 times 10 minus 7. 5 times 1 minus 5. Factor out the 7, you got 7 times 10 minus 1 plus 0. And you end up with 7 times 9. So you ended up with 9 times your first digit of your number, 7. Okay, let's look at it more abstractly. Start with a 2-digit number AB, where A and B are both digits from 1 to 9. Subtract the sum of A plus B. Do the same process we did above. Distribute, write AB as, the A stands for A times 10. That's something that Ma and Pa Kettle could have used. And the B is B times 1. Distribute the negative sign. Regroup the A times 10 and the negative A. Factor out the A, 10 minus 1, and you end up with A times 9. So you'll always have 9 times your first digit no matter what. And the key is you're subtracting that B and that the B's go away and become 0. You always have 9 times your first number. So the little trick they threw in is 99 and 9. You don't have that. So if you're looking at the table and looking for multiples of 9, you might get thrown off by that little discrepancy.
Well, and also it cleverly removes this table, so you're not possible to even see any patterns that you can.
And it makes a new table every
Makes a
time,
new
every time you
table,
do
right.
that.
So let me get this straight, they're multiples of 9?
Yeah, you'll always have 9 times whatever your first digit was. If your first digit is a 3, you'll end up with 27. If your first digit's a 4, you'll end up with...
How could that apply to any number you picked though?
Well, the A in here stands for, there's 10 of those, right? Because that's a 3, that's 30, right?
Right.
And the B is just times 1. And you minus the A and minus the B. So the B and the minus B go away. You're left with 10A minus 1A, which is 9A. So you'll always have 9 times your first digit.
There's a third multiple of 9 in the chart that doesn't have the same symbol.
The
Why doesn't
0.
it have- Yeah, why doesn't it have to have the same symbol?
We get 0.
You couldn't do it with a 2-digit number, yeah.
How does it guess which symbol to use?
Well, it puts the same symbol on all the multiples of 9 that you could possibly get, and they know that you'll end up with a multiple of 9, so everyone will be staring at the same symbol.
They shuffle them around and keep it looking fresh.
Yeah, to keep it looking fresh.
So it's a different one, I mean, potentially each time. It's a different symbol that's on the multiples of 9, but it's the same for every multiple of 9 except those 3.
So we have a challenge problem for you.
How,
Do you
but
think-
it picked 3 different symbols.
Right, each time you do it, there'll be a different symbol on all the 9.
That chart isn't the same each time.
Right, it generates a new chart, but it has the same feature that all the multiples of 9 will have the same symbol next to them.
It was spooky that the second time we did it, we got the backdrop image, which has been consistent throughout. We got the yin yang.
Ah,
I felt
yes.
like they were pushing something on us.
Ah, yes, yes.
I'm skeptical.
Agenda.
Well, okay, let's see if we could create a virtual mind reader for 3-digit numbers.
Ooh, yes.
Well, actually, can I ask?
Yes.
Can we just generate a new, I don't trust you now.
Oh, you don't trust me?
Now that I see on this particular one, all the multiples of 9 have the same, but you generate a new one.
Okay, well, focus on that symbol. Okay, focus. Okay, it worked again. Yeah, how do we turn the volume down?
Everyone recognize that sound as the beam me up sound on Star Trek?
Yeah.
All right, let's look at multiples of 9 on this newly generated chart. This little alien figure here. Notice alien figure?
Round circle with the antenna.
Yeah. Do you believe me now?
Well, let's see. We gotta see if it works.
Okay, all right, focus. Oh yeah, that's much better volume.
So
Okay.
that's the same symbol as you just showed before?
Mm-hmm.
Well, no, it's a different
No,
symbol, but it's the
different
symbol
symbol.
that's next
That's
to the
associated
multiples
next to
of
the
9.
multiples of 9. So now it would be a
The
cross.
sign would be the cross.
Cross. There's another one, 36, cross.
This would be a cross. See, so no particular religion is pushed here.
Gosh, why won't that click with me? I might have a sleep on it.
That's all right, check it out afterwards.
All right,
Okay, so,
let's
yeah.
see. So, okay, do we need to move
Go
on, or
ahead.
can we do? Okay, so let's try to do a virtual mind reader for 3-digit numbers.
Three-digit number, how would that work?
How does that work? All right, let's see.
Multiples of 9.
We are reusing our transparencies. Dr. Torrey, should we use the back of them?
Yeah, because, right, you can use both sides, right?
All right. Here's our 3-digit number. Let me write there. Let's see if it works. So we're going to take the sum of those 3 digits.
So what does the A stand for?
What does the A stand for? Yeah.
100.
100A.
Okay.
All right. What's the B stand for?
That's gonna be, let's see.
Let's distribute the minus sign through. Can you guys do a little bit and see if it works out? What do you
Combine
get?
like terms.
Yeah, where's that?
Combine terms.
You got 100 A's, take away 1 A,
29A
and B's, take away 1
plus
B.
9B and minus C.
No, the C's cancel, right?
There's 3 C's, there's a plus.
There's a plus C and a minus C.
Okay, they're gone.
How come I don't?
Which is 9 times 11 A plus B.
Oh, I wrote it twice. Okay, my bad.
You factor out a 9.
We're line groups too.
It'll be a multiple of 9, just be a much bigger table.
Yeah.
And a bonus question, which numbers couldn't you get? Which multiples of 9 could you not get? That's, well, think about that.
Okay, all right,
That
that
might take a while.
Sam will have a prize for you if you turn up in his office someday and tell him the answer to that.
Yeah.
B has to be a 1-digit number, right?
Yeah, A, B, and
Yes,
C.
A is a 1-digit number, B is a 1-digit number, and C is a 1-digit number. And I guess should we say that A can't be
A cannot be
0? A cannot be 0. A real true 3-digit number.
Well, it still end up being a multiple of 9. though,
Yeah,
right?
that's right. That's true.
Historically, maybe people might want to look up, I don't even know if it's on Wikipedia, you probably know. This is based on something called casting out nines from years ago before good calculators and so on. It's a way to check double entry bookkeeping. So,
Google it.
casting out nines.
Excellent. Okay, okay, all right. More
All right.
magic.
All right, more magic.
Amazing, magical.
Dr. Ford.
Dr. Ford.
Okay, so let's see. What's this one? All right. So everybody choose 4-digit number. And unless you're good with 4-digit arithmetic, you might have to write this down. So choose a 4-digit number. We did 2, 3, now we're up to 4. But it's different this time. Okay, so now scramble its digits. And then of those 2, now you have 2 4-digit numbers. Subtract the smaller one from the larger one.
Can't have a vacuous scramble? Or can?
No,
If they're both the same size.
Well, they
I said scramble.
really did scramble, they couldn't be the same size.
So,
Well, it should be.
so
It was like a number.
Oh, yeah, they had a
3,
repeated
3,
digit.
and you
So they have no
scrambled it
repeated
and it's the
digits?
same.
yes. So let me think. So you're not going to be able to do my next instruction if the 2 numbers here are the same. So if your 2 numbers are the same at this point, start again.
Should they choose a 4-digit number with distinct digits?
Yeah. They don't all 4 have to be distinct, but
But the scramble has to be distinct.
the scramble has to be distinct from the original. Let me know when you've got your subtraction completed. Okay. Everybody got your subtraction done? So choose one of those digits, any digit in the difference of these 2. So you've now got an answer to a subtraction problem. Circle one of the digits, but not a 0. It's already a circle. Okay. Take the other 3 digits, not the ones that are circled, and somebody tell me the resulting 3-digit number that you get.
830.
830. So I'm proposing that I'm going to be able to tell you that 4th digit, the one that you circled. So these 4 digits, you took one of them out, scrambled the other 3, get this number 830. So I'm going to say the digit you circled must have been a 7.
That's not right.
All right. Somebody else want to give me a 3-digit number that you had at the end of all this?
702.
702. So that digit you circled must have been a 9. That works. Good. None of you have learned to shut your minds off from my mind reading yet, so this is good.
I got 7, 2, and 1.
You got 721 was the 3-digit at the end?
Yeah.
Okay, so your circle digit must have been an 8 if I'm reading your
Yes.
mind correctly. Okay, good. Of course, your paper was right there. Anybody? Anybody else got one for me?
990.
990? I'm sorry?
990.
Okay, so your 4th digit must, you think now? You're trying to confuse me, aren't you, with your thoughts here? So that 4th digit must have been a 9, I believe. So anybody think they can sort of read one of your, colleagues' minds here? Okay, so Dr. Wu is going to try to read somebody's mind. So somebody give a 3-digit number. Okay, right behind you, Dr. Neal has one.
Her number, Penny's number is
144?
Number is 144.
9.
Five? No? They're more intuitive apparently.
So what were the mind readers we had? What did you guess, Dr. Wu?
I guess I was just adding the last 2 digits together.
Ah, okay. What else did we have? So did somebody?
These two guessed correctly.
Okay.
Can I
What
try
was
to
your
read
answer
someone's
there?
mind?
What was your answer there?
9.
9? Okay, so Canyon said 144, and 9 turned out to be correct there. You want to give it a shot? Read somebody's mind? Is that right here? She's got a calculator app. That doesn't sound like mind reading. Anybody else? So are you two ready to read some more minds? You think you can read some more?
Sure.
Okay, somebody else give us a 3-digit number you've got. 680. Oh, I got it. I already read his mind. What is it?
5.
I'm going to say 4.
680.
I just dropped out.
So we had a 5, but that was not.
4. Sorry.
Okay, so
You gotta do a rhythm.
okay, so 4 was correct with that. 684 was correct. Anybody else want to give a? Let's see. Anybody else want to think they have a method to? They've managed to tap into the brainwaves going around. Okay, you think you can do it?
What happens if...
Well, oh, okay. You want to ask a question?
Yeah, I was going to ask a question. What happens if you can't really scramble the numbers? Like, can I say 10? Is my ending 3-digit number?
Sure, it certainly could be. And then when you scramble the digits, you could just get 1, or you could get 100. I mean, so in that case, the digit that you erased, the digit that you circled, I believe, brainwaves is an 8. Okay. So, somebody else ready to give it a shot? Okay. So think back to the last couple of tricks. What's the kind of key piece to the last trick?
Subtract the smaller from the larger, I think. Because I'm 6 plus 8 minus 0 and equal 14. If I subtract 10 from that, I get 4. The key here is 10. I got 7. 7 plus 2 minus 1 equals.
Okay, we'll keep experimenting with that. But think back to the last trick where the website was reading your mind. What was the key piece going on there?
You're using the multiple.
Yeah, so what do you know? What's the relationship between a number and the sum of its digits?
It's 1,000 times 4,000.
Yeah, when we looked back at numbers and we broke them down, we had a nice relationship between a number and the sum. One way to say it is that the number minus the sum of the digits is a multiple of 9, right? So more generally, if you add up the digits of a number, that'll tell you how much more than a multiple of 9 the original number was. Right? If you take 97 and you add the digits, you get 16, and then you do it again, you get 7. That means the original number was 7 more than a multiple of 9. So, so if I have two numbers that have the same sets of digits, let me see here. Okay, so I was able to tell you that. Okay, so we had a couple folks who were able to read minds, and then So I'll do one example of a really tough mind reading here. So write down a 9-digit number and do the same thing. Scramble and subtract. I just need one or two examples of this, so give it a shot. A 9-digit number, scramble it, subtract, remove one of them, not a 0, and then tell me the other 8 digits you get. In any order.
Move one digit and give you the rest of them?
Yep.
They're all zeros. All the rest of them are zeros.
The rest of them are zeros. Okay. Anybody tap into the brainwaves going around here? He's thinking about that digit? I hope he's thinking about that digit. I might get it wrong. So I think the digit that he circled must have been a 9. Is that correct? That's true. Okay, good. Anybody else got a 9-digit number? I mean, 8 digits you want to give me? What's that? Yes, yes, yes. I mean, with all zeros, you might think that was just some trick or something.
I'll give it. 8, 6, 4, 1.
Wait, slow down. Okay.
8, 6, 4, 1, 7, 5, 2, 2.
Okay, if I remembered all those correctly, and I'm reading your brainwaves right, I think it was a 1. Well, okay, give me the numbers again.
8, 6, 4, 8. Sorry,
Okay, either that or check your arithmetic, right?
yeah. Sorry. Oh, we do the same thing? Yeah, okay,
So, you circle this one?
I said to you.
8, 6, okay.
8, 6, 4, 1, 7, 5, 8.
Okay, read it to me slower. I'm too slow with this.
8, 6, 4, 1.
Got that.
7, 5, 3, 2.
Then what must have been a 9.
Yes. Yes.
So this is a clue. Anybody?
I think I can do it.
Anybody? Okay.
So you have to beat me one.
You want to?
Number one.
Okay, you want to try it with a?
Digit number?
Yeah, I'll give you my 8 digits. 192001111.
192001111.
Yeah.
So 3 or 6.
Right. Say it again. Say it again. 192.
192001111.
If it's not a 3, I think you better check your arithmetic.
That's what I thought, and that's why I was so anxious to give my number.
All right.
So you cannot read a liar's mind.
There you go.
He's thinking about golf.
I can't read the mind of somebody who messed up their arithmetic.
I scrambled, I put a new number in my second.
Give me the
All right, I withdraw mine.
So it would be a 3, but I would say.
It would have been. Yep. Would have been a 3. So you can read what his mind should have been putting out. Okay. All right. So let's take a look at this. Oh dear, I left that in. All right. So let's take this 4-digit number as an example. So this looks familiar, right? We write it out. Sorry about the lame transitions. So if we break it down into these multiples of 9 plus these things, here you see the sum of the digits, right? So just imagine if I scramble this number, then this piece of this expansion isn't going to change, right? It'll be, the terms will be rearranged in there, but it'll still just be the sum of the digits. So, and the stuff in these parentheses, I should say, is all a multiple of 9, right? So, what can you say about the difference of two numbers with the same digits? Well, we're going to take something of this form, and then we'll subtract another thing that looks similar with a bunch of multiples of 9 and the same sum of the digits and then subtract the 2. So what are we going to end up with? We'll end up with a multiple of 9, right? Because the sum of the digits part will subtract away, and all we're left with is a bunch of multiples of 9. So when we subtract two numbers with the same digits, we're necessarily going to end up with a multiple of 9. And so how was I able to read minds? If, for instance, you gave me 321, those add up to 6, and I know the total number must have been a multiple of 9. And as we saw, numbers are multiples of 9 if the sum of their digits is a multiple of 9, so I knew the missing one had to be a 3. 321 is 6, and to get up to a multiple of 9, I needed a 3 to do that. So the sum of the digits has to be a multiple of 9 after you do that subtraction. And of course that doesn't work just for 4-digit numbers, it'll work for any number. So here's this example worked out. 5, 3, 4, 6, and scramble them that way, you get 1692. And if we break them both down, we get down to 9 times something plus 0. And so the digits of 1692 add to 18, so if you leave any one of them out, I just have to figure out which one is missing to add up to 18. So why did I have to prohibit you from not circling 0? Prohibit you from circling 0.
You might not know if we had a 9 or a 0 that we avoided.
Yeah, if the numbers you give me were, 9, 7, and 2, that adds up to 18. So the 4th digit could have been either a 0 or a 9. So I had to make sure it wasn't a 0, so that whenever you gave me digits that added up to a multiple of 9, I could just say 9 was the
Zero's
one.
always a circle, so a circle would be a number.
Exactly.
So
Yeah, that's right. Circling a circle doesn't make any
So
sense.
what this was circled in 9, like 18.
Yeah, exactly. If in this case you circled the 9 and you gave me 1, 6, and 2, that adds up to 9. And so because I told you not to circle a 0, I would know that the number you had left out was a 9. Okay, so there are some great internet resources for math and movies that we started out with, and I thought I'd end with one more clip from a movie of a rather disjointed math class. Let's see. Yeah.
All right. Now, who can explain Newton's method and how to use it?
You can use it to solve nonlinear equations.
That's impressive. That's really good. I mean, I'm very impressed by that, especially since my class is called Nonlinear Equations. All right, now somebody tell me something I don't already know. Anyone? Bueller. Anyone? Bueller.
Newton stole it.
I'm sorry?
Newton stole it. Joseph Raphson published the same method 50 years ago. If the start value is too far removed from true zero, then it fails.
I'm sorry, what's your name?
Ben Campbell.
Ben. So Ben Campbell suggests that Joseph Raphson was the original author of this method. Well, if that's the case, then why didn't he get any credit? Well, for one thing, Newton had a better publicist. And for another, after 1700, we know very little about Raphson other than the fact that he discovered the Kabbalah about 300 years before Madonna. All right, now, let's give Ben a chance for some extra credit, shall we? We're going to call this the game show host problem, all right? Ben, suppose you're on a game show, and you are given a chance to choose from 3 different doors, all right? Now, behind one of the doors is a new car. Behind the other 2, goats. Which door would you choose?
Door number 1.
Door number 1. Ben chooses door number 1. All right, now, the game show host, who, by the way, knows what's behind all the other doors, decides to open another door. Let's say he chooses door number 3, behind which sits a goat. Now, Ben, the game show host comes up to you and says, Ben, do you want to stay with door number 1 or go with door number 2? Now, is it in your interest to switch your choice?
Yeah.
Well, wait. Remember, the host knows where the car is. So, how do you know he's not playing a trick on you, trying to use reverse psychology to get you to pick a goat?
Well, I wouldn't really care. I mean, my answer's based on statistics, based on variable change.
Variable change, which you just asked you a simple question.
Yeah, which changed everything.
Enlighten us.
Well, when I was originally asked to choose a door, I had a 33.3% chance of choosing right. But after he opens one of the doors and then re-offers me the choice, it's now 66.7% if I choose to switch. So yeah, take door number 2, and thank you for the extra 33.3%.
Exactly. People, remember, if you don't know which door to open, always account for variable change. Now see, most people wouldn't take the switch out of paranoia, fear, emotions, but Mr. Campbell kept emotions aside and let simple math get his ass into a brand new car, which is better than that goat you've been driving around campus. All right, everybody, that's the end of the day. Thank you very much. Your graded papers are down here at the end. You can pick up.
So, you can really learn something from your math class. Useful, right? From the movies,
Kevin
too.
Spacey.
That's right, Kevin Spacey. So, I think that's it for our tricks.
Yeah.
All right.
Thank you. Back with speakers. If the rooms that we heard earlier are true, there will be pizza in the math lab, which is in room 108, just down that way a little bit. It's usually here on time, so let's go get some pizza down the hall. So thank you.